David's getting the charts pulled up, I want to say it's great to be here with you today. I really enjoy hearing these presentations. I particularly enjoyed hearing Bill Baruch talk about the data coming back from Kepler. He and I worked together on that mission in a different capacity about 3 or 4 years ago, and it's really neat to see Goldilocks going and checking out the House of the Three Bears there. Some of these things are too cold, some are too hot, some are just right, some are too big, some are too small. I just hope when we go, we don't run into the bears. Yeah, that was my icebreaker. I'm going to talk to you today about something that I hope you can get excited about. I know walking up here, there's a lot of folks that have a lot of different ideas about how you go into space and how you get there. I spent the first 11 years of my career on space station, and then about the next 9 or 10 working science missions from Gravity Probe B to Discovery New Frontiers, ultimately becoming Deputy A of Science when Alan Stern came in to run that office. And I spent, the funnest part of my career was really that middle section, because a lot of the folks you're hearing from at these events, I got to be there with them when their dreams were realized. One of the most formative moments in my career, I sat console for the Phoenix landing at JPL, and then got on a plane that night and went down to Arizona with Peter Smith, and sat in a conference room when the pictures started coming up on the screen of the North Pole of Mars. And it was an amazing experience for me to be looking at something as if I was a virtual explorer of Mars with this group. And these guys just had tears coming down their eyes. They were seeing things that nobody has ever seen before. And so it's great to be here today to talk to you about Mars and about the Space Launch System. One of the things that people get a little confused about is whether Mars is the mission or not. I'm here to tell you today that Mars is the mission from a NASA perspective, and this is just some examples of that, whether it's the President's space transportation policy, or the appropriations and authorization language you see out there, or even NASA's 2014 plan. You see that humans to Mars is the ultimate goal. That is, and it's been the goal for 40 years. We almost never disagree that we want to put human feet at Mars at some point in the future. The other thing I like is this idea of humans from a scientific perspective. This picture was actually done by a gentleman named Dan Durda from Southwest Research Institute, who is a geologist. I'm a big fan of exploration from a historical perspective. I love the idea of Joseph Banks traveling around with Captain Cook, a real biologist, a real botanist that actually helped the crew survive scurvy, but in return he got to see things and learn about fauna that no one had ever done before. Those missions also did astronomy. Captain Cook actually has in his logbooks pictures of the Venus transit across the summit. He was chartered to do so by the British Royal Society. And so when I think about building a rocket to go to Mars, I think about this being a geologist who is out there actually finding that special rock that maybe the robot would miss on its first pass. But Mars is hard. You may have seen this chart recently coming out of headquarters. If you're going to put humans on Mars, you're going to need radiation protection. You're going to need some form of habitation module along the way. You're going to need a lander, and then you're going to need an ascent vehicle. And if you talk to the JPL guys, they'll tell you that Curiosity really kind of pushed the limits of our current abilities to be able to land mass on Mars itself. Also, we have the International Space Station, and we've put people in space for long periods of time, but we're only hours away on the International Space Station, and we're only a couple hundred miles from Earth. Mars, you're talking years. If you want to go and come back in particular. And so there's this idea that we need a proving ground. We need something there before we actually go to the surface to start to develop these longer term ideas of becoming more and more Earth independent before we actually go for score. And I know that's debated out there in the community, but I can tell you this is where NASA's thinking today. Also, Also, I'll tell you, this is being discussed on an international scale. There's a group called the ISIWIG. It's an International Space Exploration Coordination Group. And they put their roadmap out this year. It's most of the human spacefaring nations, most of the folks involved on the International Space Station. The idea being to utilize space station more and more to prove out some of these things. You see that thin blue line there in the middle. You know, a lot of people think, well, NASA's not really friendly to the commercial crew and cargo folks. And I actually was out at Space 2014, and they asked the panel, and we were all on the panel, all the NASA guys and all the commercial crew guys, and the question was, well, what's NASA doing to help them, or what can it do more? Well, NASA built the International Space Station. It is the market that is creating this commercial crew and cargo armada out there that you see coming along today. Those companies, a lot of them are surviving and moving forward because of what NASA's doing to fund them, and because we've created this market of cargo and crew to the space station itself. In the meantime, if you follow all the robotic Mars stuff, you know, there's going to continue to be Mars exploration robotically. We've got a lot more to do there. I know you guys are talking about that here at the conference today. But this international group, this is the roadmap they came up with, and you see down here at the bottom the human stuff, but what you see down there is that multiple locations in the lunar vicinity. The idea is either the moon itself or a Lagrange point or an asteroid that is brought back into a Lagrange type territory before you actually get out to Mars itself. And we've done a lot of studies, and if you're going to move out into the universe and do deep space exploration, I submit, I think you're going to need a pretty big, powerful rocket. And I think the more you want to do that, if you really want to colonize and you really want to have people out there, people are a pretty needy species. If you go to the port of Los Angeles, and I actually drove through there to get here this week, you'll see that the ships are bigger than they've ever been. Every generation of cargo ships are getting larger and larger. Trains are getting longer. Planes are getting larger. The A380 is the largest plane ever built. And so to supply people, once you get there, you're going to need pretty large cargo capability. And so we're starting with a 70 metric ton rocket. This is enough to take the Orion capsule, and Mark Geyer will be here tomorrow. He'll talk to you about that, out beyond the lunar area. And then when we evolve it with the upper stage and get it up to the 10-meter fairing, you can now do an 800 metric ton mission to Mars, the old, what we call DRAM-5. Larger rockets have a lot of benefits. First thing you get is a lot more departure energy. If you look at the bottom of this chart here, you see that kind of yellow region down there. That's the largest capability we have today in the world. When we have this 70 metric ton rocket put up, you'll see that green line there. When we add the upper stage, you get up to the blue line, and when you add the advanced boosters, you get up to the purple line. And you can see for a cargo mission or even for a flyby mission, the kind of masses you can take with that to those C3 values. Interestingly, the folks that are doing the Europa mission, Tom Gavin and the folks at JPL, Barry Goldstein, who actually worked the Phoenix mission, have come to us saying, we actually like what you can do for us on Europa, because if you take a principal investigator who's maybe in their late 60s and working that mission, and you think of how long it is before they actually fly, and then you think on an existing rocket today it takes 7 years to get there, this rocket can get you there in about 2.5 years. So it becomes really interesting to them in terms of scientific return, because you can fly the mission direct, but also you can trade that speed for mass and volume, and you can start to do more and more. Maybe you can put a lander on it and do more. My friend Alan Stern, and he and I have a lot of scar tissue getting New Horizons launched. You know, we launched that thing back in 2006, and it doesn't get to Pluto until next year, and we're going to get a couple days best of science, full science, as we fly by that thing at like 56,000 kilometers per hour. He's very interested in a New Horizons 2, where you might put another stage on that thing and slow it down and go into orbit. And that's kind of the natural progression. You know, you fly by, and then you orbit, and then you land, and then you rove, and then you bring humans. And so he's having us look at what we can do for New Horizons 2. You guys are probably familiar with charts like this. I really like this chart because even for robotic missions, we all have to acknowledge that Mars is hard. There's a lot of red stars around the outer loop here. These are countries that tried to do missions to Mars. A lot of failure. As a matter of fact, and you may correct me, but I think the only non-American mission to actually make it to the surface was Mars 3, and even that was like 20 seconds of data, and then it went away. What I like about this chart is that this rocket, in the 130 metric ton capability, can take every mission that we've ever flown to Mars in one launch. So when you start talking about game-changing capability, think about the kind of scientific return you could do in a mission like that. So another one that came to us was Dennis Tito about this time last year. Came down to Huntsville and started asking us about his Inspiration Mars mission. Could we do it? We did a lot of studying of that thing, and from a rocket perspective, we could actually close on this 2018 mission with our upper stage. The 2021 is actually also an interesting window. It's actually a little longer but less energy to get there. But it's the kind of thing where, you know, if you guys have followed his mission, you put humans at Mars in a single launch. And to me, that is inspiring. You know, you think back to Earthrise and the pictures we had and what that did to us and how we thought differently about the moon mission and actually putting feet on the moon. This could be a very similar type thing for humankind at Mars itself. The other thing is just when you start talking about liftoff capability, again, every rocket out there today, you kind of see the mass and volume capability. When you put the upper stage on this thing and put the 10-meter fairing, the mass and volume capability is really just going to change the game in terms of what we can do in the long-term space. Again, payload volume, you look there to the three on the right, you kind of see existing capability. You know, another guy that came to talk to us is Robert Bigelow, and I've been out to his place out in Las Vegas. You've probably seen his 330 module. He's got another one, and I forgot the number, but it's twice the volume of the International Space Station. With our big rocket and big fairing, we can launch that entire thing in one launch. And so imagine now that to build the International Space Station, it took a long time, more than 10 years, and 25 shuttle launches and 4 Russian launches to assemble it. Imagine building a space station with twice as much volume in one launch, and having the ability to support a crew of 16. That's pretty game-changing as far as I'm concerned. Mars sample return, a couple years ago we went out to Big Sky, Montana and talked to the Mars folks when they were reformulating. One of the benefits we gave them is the idea that you could do the entire sample return mission in one launch instead of 4. And I understand they're kind of heading in a different path now, but just to kind of put it in perspective for you, if you want your sample return from Mars and you want to be able to do it in one launch, this capability can do it. One of my favorites, this is by the way one that I really like, and I've liked it for years. As we say, Mars is hard, and getting to the surface of Mars is hard, and then getting back off the surface is hard. But if you can get to Phobos or Deimos, there's a lot of things that are really kind of cool about it. You can kind of dock up to it. You don't really have to do a hard landing. You might have to be careful how high you try to jump, because I think the escape velocity is like 25 miles per hour or something like that. But what's amazing to me about it is when you talk about that Earthrise picture, you can kind of see on this picture, the top right there, Mars up on top. That's what it looks like from the surface. You're only like thousands of miles away, not hundreds of thousands. So Mars looms very large above you there. One of the things I really like about it is if you were to take the rover and give yourself telepresence to be able to actually drive the rover from the moon, you don't have that 23-minute delay. So the geologists, even though they're not on the surface, they actually have real-time reaction capability with the rover. So it's just like you do in telemedicine today. There's not a long delay. And so I like the idea. It's half the delta V. You're there. You don't have the atmosphere, but you can also do geology on Phobos Deimos yourself. But I also think if, especially with the country, and if we do things in a traditional way, we're subject to the whims of changes in Congress and the administration. If you get to that far, then you can sell the next step within a single political cycle. So anyway, that's one that I really like. And then I mentioned the DRA-5. This is back during the Constellation program. If you were going to go with a full crew contingent and bring them off on the live, we certainly can close that mission as well. So I really want to tell you kind of how things are going. We've been at this thing now for about almost 4 years now. Big picture, we said 4 years ago we would be a critical design review on the Corps this November. I'm glad to report that we actually completed that last month. And this was not some... You know, one of the things that I learned in working in the science world was the importance of actually setting a schedule and doing things you said you were going to do. We moved some mountains to get New Horizons off in 2006. When I first stepped into the Discovery program, it was not on the track to get there. And we went to the administrator and pulled a lot of strings to make it happen. And I watched Alan, the way he managed, and the way he never took no for an answer. I will tell you, you've got a pretty motivated team who is not taking no for an answer. They're clawing and fighting every day to get this thing ready on time and on budget. So our critical path is through the core of the vehicle itself. The CDR was clean. Over 1,000 people came and looked at all the data. There were 200 rids. To put that in perspective, when I worked Space Station, we had over 3,000 rids at the PDR and CDR. When we worked Constellation, Ares 1 had over 3,000 rids. So it's an order of magnitude less. This is a good, clean package and a good design. We just completed this week the CDR on the boosters. We've got 2 more CDRs, the engines, and then the interim upper stage heading into the winter and early next fall, and we'll have the vehicle CDR in the spring. As far as building the hardware itself, again, the critical path runs through the core. We've completely retooled Michoud. It used to take over 30 tools and about 1,200 people to make an external tank on the shuttle. This has the same diameter, but instead of 160 feet tall, this core is over 220 feet long. We built it with 5 machines. They're all self-reacting friction stir welded. The largest tool starts up this week. It's 170 feet tall. It's accurate within 0.02 of an inch, and it can pop out an entire hydrogen tank. And so we're doing this with about 300 people now. And so we've really found a lot of efficiencies. And with the extra space at Michoud, we're actually selling off that space. There's movie companies in there filming. If you see Planet of the Apes or Ender's Game or the Expendables, all those movies are being filmed now inside of Michoud, which helps offset our rent. There are other companies in there. Sierra Nevada's in there. Orion is doing work in there. Lockheed is doing some commercial propane work in there. All that's doing is offsetting what was a pretty big bill for NASA, which used to be $120-something million a year. We've now got that gap to about 13, and we're heading to 0 for the next couple of years. And so that's all about making it more affordable. So the core is being designed to be built in a very affordable way. We do have these heritage boosters out there. Those things used to be really expensive. One of the expensive things was because they were reusable. We were actually spending about $75 million a year to refurbish, strip them all back down to the metal, and put them back together and put all the parachutes in there. We actually had what we called the Navy, the NASA Navy, where we had ships. We had our own ships to go out and get them. We've thrown a lot of that stuff away just to make these things more expendable and less expensive. The engines themselves, those are the RS-25s. What's really good about those engines is the engines we're talking about have actually flown in space before. These are very reliable engines. They're in great shape. We have enough for the first 4 flights to get going, so we don't have to worry about making the engines until out into the 2020s. The interim upper stage is a Delta IV upper stage, so when Mark talks to you about EFT-1 in December of this year, that's launching on this, what we call an ICPS. We basically have that same configuration from about here up on this launch, and so there's a lot of commonality there. That helps us to avoid a development curve, because living under a flat budget, we can afford about 1 development at a time, and our big development is through the core itself. So again, things are going pretty well as far as the critical path. We've still got 3 to 5 months of slack to our committed date to deliver the core to Stennis for full stage core testing. The B2 stand, which is where we'll put this thing, is actually ahead of schedule and on budget as well. So we're just clicking off milestones. This is a chart we like to show up in DC. We've kind of hit everything we said we would hit today. You can see some coming up. The manufacturing tooling installation will complete this month, and we'll spend the early part of December doing an acceptance test on that and getting ready. We hope to have the first qual hydrogen tank out of Michoud by December of this year. And then we've got the RS-25 engine now in the stand. One of the things about using an existing engine is it becomes a constraint to your systems engineering process, but you can't constrain everything. And so actually the inlet pressure on the engine, because the tank is taller and the vehicle flies fast, is higher than it was on the shuttle. So we're actually having to run it through its paces with a higher inlet pressure. This is also a little more efficient in delivering the locks to the engine, so we're testing out the bottom end of what we call the start box of the engine itself. Finally, we're using a state-of-the-art controller on it, so we're testing out the new controller, so that'll be tested this fall. Again, we've got our vehicle level CDR coming up next year, and then we start assembling the core and get ready to test fire. So in a year or two, you're going to start seeing this hardware show up. First, all 5 of the major pieces of the core are going to be sent up to Marshall and be tested on big structural test article stands. And then by about 2016, you're going to see this core go out to Stennis. And it's actually a proto-flight test. That same core will be shipped down to Kennedy Space Center after that testing and be ready to be integrated into the stack. So that's really all I had to tell you today. Again, thank you for having me here. I would tell you you've got a very motivated team that is building this rocket, down to the folks that are putting bolts together. They know when they build bolts, that's going to be put on a rocket that's going into space. They treat it with special care, and I don't mean just all the rules and regulations. I mean they take a lot of pride in what they do, and those folks are all over the United States today, and they're really excited to be part of this. And so we're just glad to be here and glad to be making progress. Any questions y'all might have? December of 2017, my hardware will show up to support that flight. Yes, ma'am.
What's the approximate per flight or per line cost of this rocket?
Yeah, we've been saying about 500 to 700, depending on whether. So I'd say about 500 to 550 in this configuration for 70 metric tons. When you add the upper stage, we might be in the 600 to 700 range.
Talking millions.
I'm sorry?
Millions.
Hundreds of millions, yes. You got anything cheaper? Yes, sir.
What did you say the tonnage to each location in your solar system would be for SLS?
It depends which locations you mean. If you're talking about translunar, it's 25 metric tons translunar. In the 130, if we go back to here, we can actually get you the chart. If you see the cargo or flyby missions to Mars, you just take those 2 dotted lines up. So if you're at the 130, you're in the 45 metric tons for a cargo mission, or for a flyby with humans down to the 28 metric tons. Yes, sir.
Any implications for the complex relationship with Russia?
Not directly related to us. So I'll try to speak as much as I know without being the official voice of mass, if you will, but I have been following it. The space station itself continues to go very well. We continue to have folks that are going to Baikonur and supporting the launches, and the folks on the station are working very well together. An implication right now in the industry is the fact that the Atlas V vehicle uses RD-180 engines, which are Russian. And so there's a lot of discussion around should the United States have a backup option for that, or should actively be pursuing additional American-made large RP engines. We can benefit for that because in the Evolved rocket, we're going to compete the future for the boosters themselves on the side, and those could be solid or liquid. If they're liquid, most of the designs we've seen are large RP engines, and so that would benefit us as well. Yes, sir.
Yeah, you talked about being on schedule, but there was a recent GAO report that raised concerns about cost and schedule risk of falling behind schedule. Can you explain what the GAO saw that you don't see?
Yeah, I'll tell you. Well, first of all, they saw some things a couple of years ago. Some of their data is now obsolete. We saw some cost risks in FY14 and 15 in particular. And 14, if you may have noticed, our appropriations at the end of the year in the last 3 years has been several $100 million above what the President's budget request. And so they were seeing that if we didn't continue to get above that there would be significant cost risk. So of the $400 million they talked about, 250 showed up last year as part of 14. And if we can believe either of what we've seen in the House and the Senate on the bills we're seeing come out, there's another $150 million right there. So it has to do with a gap of if you don't receive the appropriated levels, you could see challenges. With respect to risk, it's a tough thing because the way you kind of look at these things is you do statistical analysis around your schedules and things that could go wrong. So you basically look at a low and expected and a high value for your schedule for every major task. You basically roll it up to a certain number of tasks, and then for the cost of each task as well. And then you run a Monte Carlo analysis. I will tell you that that's not always accurate, and if those things do come true, you need to replan, but to me it doesn't change a basic program management tenet, which is to hurry every chance you get. And it's one of those things I learned from some of these planetary missions that have to launch in a window is they don't pay attention to those things. They hurry every chance they get. And so far that's paying off for us. Yes, sir.
How was NASA looking at communications, all that stuff, just like in here, China, what
I'll just say this, now that would be stretching me beyond my job. In terms of partnering with other countries, I can tell you on the rocket piece itself, we have a couple of areas where we have been exploring partnerships, particularly with the Japanese on upper stage engines. The Swiss are very interested in partnerships with fairings. We have had some discussions with ESA with respect to potential collaboration on upper stage and things like that. But in terms of China on the rocket itself, and you can imagine right now it's not probably a good time to be bringing that up. So in general on the rocket, that's been the limits of our partnership. Mark will tell you that we're already partnering with ESA on the service model for Orion. I think that ISIWIG report might be a good thing to read because that's where a lot of the other spacefaring nations come in and talk about the things they would like to do to collaborate. And again, it's a lot of the same players that you see on the space station, which includes the Russians. China, to me, is, I think, something I want to get in the middle of in terms of debate. I think that debate's happening above my pay grade. Any other questions? Yes, sir.
Will be ready this SLS system for the integration Mars project?
I didn't hear what you said. I'm sorry. You said, would I be ready for the Inspiration Mars?
Yeah, the rocket will be ready for the Inspiration Mars project.
Yeah, if let's say it this way, I can build a rocket that can be there and ready to fly at Inspiration Mars. There's a lot of policy involved above my pay grade and negotiations and agreements that would have to be made for that to actually happen. I'm a fan of the mission. I like it personally, but I don't make those decisions. Yes, sir.
We got a question from the chat room from Nairobi. She's asking, how long before the SLS can be mass-produced?
I would say the way we're designing it is to be optimized around about 1 flight per year. We can surge for 3 flights a year, so for like a campaign, with the current hardware we have. And so I would say that becomes a matter of money because you have to have the money to build the non-recurring cost for each of those units. But beginning in about 2018 or 19, you could start going 1 a year, and depending on how bad you really wanted to, we could pop, 2 out a year, maybe 3. If you wanted to expand the capability, if you have that kind of money though, I think you really need to start talking about another line of equipment to build another set of cores through and stuff like this. It's like any factory. There's a book by Eli Goldthwait called The Goal, and it tells you about how you actually optimize your factory to get rid of choke points. And I think probably the choke point will be putting cores through each sheet. And where's, hold on just a second, Mr. Dubrin, you tell me when people want to eat lunch. I'll keep asking questions as long as.
3 more minutes.
3 more minutes.
How many dollars and how many years would you estimate between the 70-ton and the 130-ton version, and how would you see the likelihood of proceeding to the second stage of the project, or the risk of just getting stuck at the 70-ton and not getting the additional funding?
Okay, so I can't tell you the exact amount of dollars because it's really dependent on how many dollars per year you want to spend. So an optimum project development curve wants to look like this. The more you try to flatten that, the longer it takes and the more total what you actually, it's not like just expanding a balloon. It's like expanding and heating up the balloon, so it actually costs more. We are actually formulating the upper stage as we speak. You may have read out there, we've tasked Boeing to look at what it may cost to actually do the upper stage and get it going by the second flight. So if you get to the upper stage, and what we've been looking at is what we call a dual-use upper stage that's used for ascent, plus the TLI injection as well. You can actually get to 123 metric tons with just one more development. And so the boosters become, when you actually want to put humans on the surface itself, you might have a discussion around the boosters. So we could have the 123 metric ton version by 2021 with the right dollar figures. Yes, sir.
Are you currently on anything remotely approaching an optimum development cost curve?
An optimum what?
Development cost curve.
Actually, I'll say it this way. We got, you may remember, the whole government shut down last year for a month. That wasn't very fun. And we did not have an appropriations until into January of 14. We got very close last year to deciding we may have to slow down the critical path. And I would say within days. And it was the kind of thing where we had met and decided the appropriate thing to do would be to slow down. Because the appropriations actually came through, we haven't slowed down one bit. So we have been optimizing our critical path. Now, that said, we've been doing other things off the critical path that wouldn't be optimum for those other pieces. So, for example, we've taken the boosters and the engines down to what we call basically the floor. It's essentially sustaining them until we need to do work there. And so we take them down to the minimum so that that group is available and ready when we start coming back and flying. So that's not optimum for them, but it's good enough to get the vehicle what we needed, and we're putting the money where we need to put it. So this is all part of living under a flat budget. When your budget is absolutely flat and you're trying to develop a rocket that from the very first launch has 10% more thrust off the pad than a Saturn V, this is a big challenge.
That'll have to be the last word.
computer uses it. Let them know where it's running.
Yeah.
It's certainly not the same thing as the AES.
That's what I used to do.
Hi, Jason.
Hey there. Jana?
Jan.
Jan. Add an A. Should never add an A. How you doing today?
I'm good, and how are you?
Much better.
Okay, I saw it just streaming along there all
And
morning.
it's been streaming along. I'm actually taking up to asking questions from the chat room, and more and more. Bob's kind of getting more and more. Okay, it's okay. But back in the way, so I'm like. But we ended up plunking down an extra $500-$600. We bought that, which reminds me.
But you're still not going to stream much.